Okay, well, hopefully it's not super distracting. My dog is chewing on a bone right next to me, so we'll see how this goes. Okay, so we're on to chapter 11 now. So this is still unit 6, though, talking about angular and rotational motion, angular/rotational motion, I should say. Now we're talking about momentum. So this is actually a really short chapter. It's only 3 lessons because we combine point 1 is just an intro, it's point 2. To this concept of angular momentum, and then we just have 2 more lessons, and it's actually pretty quick wrapping up. It's going to give us a lot of time to do some practice problems and get ready for our test. Let's kind of refresh our memories back because we've talked about momentum before. So think for a moment and see if you can. What's the formula for just regular linear momentum? Well, this was P equals mv. So this is momentum equals the mass of the object times its velocity. So remember that momentum is a vector. We're talking about velocity, right? A change in direction is a change in momentum, even if we bounce up against a wall and come away with the same speed. That is a change in momentum because we do have a change in direction. We have a change in velocity. Now, angular momentum is going to look very similar. Kind of how we talked about so far in the last chapter was a lot of this stuff works similarly. We just have angular variables that we're working with here. So let's think about what the formula would be then for angular momentum. What are kind of the corresponding concepts for mass and velocity in angular motion? Well, in angular motion, we know that it's not just mass that's important. It's also the distance from center, right? We talked about how, and we know this, we're going to even talk about it more today, as we change that distance from center, that can change a lot of things. That's going to change your speed. It's going to change how difficult it is to rotate. And again, that's rotational inertia, how difficult it is to turn, basically. So we're going to replace mass with rotational inertia, which we know is kind of unfortunately complicated because we've got formulas for that as well. And we're going to replace velocity with our angular velocity, omega. So, and again, kind of weird, there's so many possible formulas in our world of physics because there's so many things we can model with math that they kind of run out of variables. So just think this is angular L momentum. Is our variable for angular momentum. Now, the nice thing is that the same principles apply to angular momentum as they do to linear momentum. So we know this is a lot of what we did in the momentum unit, that angular momentum is conserved when there's no additional force acting on an object. Again, if we have friction involved, that is going to affect things. But if there's no friction especially, or air resistance or anything like that, the momentum before the initial momentum, angular, is going to equal the final angular momentum. So this still applies. However, there are slightly different units for angular momentum versus regular momentum, and that has to do with the fact that rotational inertia itself has a separate formula, and so the units get a little bit different. So this is kilograms times meters squared over seconds. Again, kind of weird. Remember that if you are ever unsure what the units are on something, it comes from the formula. What the units are for I and what the units are for omega gets us to this unit. So let's talk about an example here of momentum. And again, this conservation momentum concept. We can change the momentum of a single object with a set mass by changing the distance from the center axis. If we wanted to change the momentum of a single object before, we had to change its velocity, right? Because again, that mass is set. We could change the mass, we could tack something onto the mass, but here, if we have a set mass, in order to change the momentum, we can change the distance from the center. Now, I'm sure you guys have all seen, actually I have pulled up already, videos of ice skaters, like you do in your spare time, just watching ice skating videos. Doesn't everybody do that? That's what I do in my spare time. And we can see an example of a change in momentum here with how the ice skaters change the distance from their center of mass. So we'll see, to start with, this ice skater starts with her leg out, far away from her body. And then as she pulls in closer to her body, notice she gets faster. and then slower again as her leg comes out, and then seriously, I do not know how they don't just get dizzy and pass out and die. I turn as a dancer, but we do something called spotting, which helps us not get dizzy, and they don't spot. I don't know how they don't get dizzy. It's really impressive. So we can see again as how that happened. The further her leg and her arms were from her body, her angular speed was slower. As she brought her arms and legs in, she suddenly sped up and her angular speed increased. That's a change in momentum. Now, again, I know it's kind of weird sometimes. We're like, why do we have to talk about momentum? Can't we just talk about how our speed changes? Remember that momentum measures something different than just a change in speed. If we were talking about a child just learning to do the spin for the first time, their mass and therefore their rotational inertia is going to be different. So even if a child and this woman here were spinning with the same angular speed, angular velocity, they're going to have different momentums because their rotational inertias are different. Again, think in terms of if that kid smacked you in the middle of their spin versus getting smacked by her, it's going to hurt more because she has a greater angular momentum, even though they have the same speeds. So try and get that concept straight. Yes, two things can have the same angular speed, but different angular momentums. So let's talk about that. My dog's really hacking away at that bone. I hope it's not too loud in the background. Oh well. So we have a figure skater executing a scratch spin, which is where she gradually pulls her arms in while spinning on one skate. During her spin, her momentum changes because her speed changes. Her angular speed increases from 1.5 radians per second to 15 radians per second. As you saw, they spin really fast when they bring their arms and legs in like that. So this is a weird question. You might not think it has anything to do with angular momentum. By what factor does her rotational inertia around her central axis change as she pulls her arms in? But rotational inertia, again, is in our angular momentum formula. So what this question is saying is her initial angular momentum, we know that by conservation of momentum, is going to equal her final. Now, again, we have this kind of inverse relationship here, so we can make a prediction. If we need momentum to be conserved, as speed increases, as our angular velocity increases, what do we think is going to happen to the rotational inertia? Again, looking back to our formula, actually, I'm going to go ahead and just copy that over before we say this. This was our angular momentum formula, I, rotational inertia, times omega, our angular velocity. So what we have here is I initial, because again, that rotational inertia is going to change as she brings her arms in, times her initial angular velocity. Equals her final rotational inertia times her final angular velocity. So this is actually going back to our conservation of momentum. So thinking again, if I increase the angular velocity, what do we think is going to have to happen to the inertia for momentum to be conserved? It's going to have to go down, right? If I increase this number, in order to still get the same thing here overall, I need inertia to decrease. And that should make sense because inertia increases with her arms way out from her body. As she brings her arms in, her inertia decreases. Now, we don't know the formula for her inertia, but that's okay. We're going to go ahead and leave it as is. We do know that her initial angular velocity was 1.5 radians per second. And there we go, good to go. Already radians per second. And again, we don't know her final, but that wasn't what the question was asking. The question is, how does her inertia change, not what is her inertia? So we're fine there. So what we want to do here is we're going to compare the ratio of her inertias to the ratio of her angular speeds. Now, let's go ahead and move this over so that we are comparing the final to the initial. Yeah, we always want to do that. When we talk about how something changes, the final should be on top, the initial should be on bottom. So take a moment to move over and move this around so that my initial rotational inertia is on top of a fraction, and then I have the other stuff on the other side. So what I mean by this is, here's our initial inertia. So I have 1.5 equals, I've got inertia final, good Lord, gonna get these all mixed up. Inertia initial times 15. So this compares, once again, my final to my initial, and then I'm gonna do the same thing and I'm gonna move the 15 over. So we have inertia final over inertia initial. Once again, this is going to tell me how my final compares to my initial. Let's go ahead and get 1.5 divided by 15. This is going to be 0.1. So what this means is that's actually our answer. That is the factor that the rotational inertia changes by. Notice that the angular speed increased by a factor of 10. The inertia decreased by a factor of 0.1. That's not a coincidence, right? Again, we have to have this change for momentum. If I change my velocity, my inertia has to change in response and in the same way. So kind of as a prediction here, if we change this by a factor of 50, so if I multiplied 1.5 by 50, I'm increasing the speed by a factor of 50, the inertia is going to decrease by a factor of 0.5, right? Again, whatever I increase by, I need to decrease by kind of the same amount. We can say it like that. So let's go ahead and try one more here, talking about how we can conserve this momentum. This one now is talking about the final angular speed. So you have an ice skater still, mass 45 kilograms, starts to spin with her leg out perpendicular to her body. So kind of in the video, we have the leg out. Her toe measures 0.8 meters from her center of mass. So we're saying her leg basically is 0.8 meters. Her angular speed at this time is 1 rotation per second. Careful with this. That's rotations per second. Always be like, wait, we need radians. She then bends her leg and pulls her foot in, with her knee now being the furthest point away from her body, a distance of 0.35 meters from her center of mass, and they are telling us how to model her inertia. This is actually the formula for a rod spinning. A human is not exactly a rod, but we're going to model it that way. So it's going to be kind of an estimation based on this model, but we can still get an idea and kind of make predictions. So what is her angular speed now? So here's how we know we're dealing with conservation of angular momentum. We have a before, we have an after, right? So we know that L initial is going to equal L final. So I'm going to go ahead and write this out with our formulas again. I initial omega initial equals I final omega final. And again, we also have a formula for her rotational inertia. So once more, I am going to go ahead and write this one more time. We have her mass, which does not change, but we do have an initial radius because that changes, right? So anything that doesn't change, we can't give an initial and a final. But the radius does change over 2. So there's our initial rotational inertia times omega I. Go ahead and write out the second half, and then we can just come back and check. Okay, so once again, the mass does not change, but we do have a different radius, so final, over 2 times omega final. So from here, it is just a matter of, thankfully, going through and plugging in. I want you guys to try it. The only thing we need to be careful about is we do need to get this in radians per second. We want to get in the habit of that. We technically don't have to do it every time, but we want to make sure that we are, just in case. We won't get marked down if we do it and they don't say to. So go ahead and change this to radians per second. and then we will go ahead and plug everything in. Go ahead and give it a shot. Okay, so her mass is 45 kilograms. The radius to start is 0.8 meters squared times her initial rotation per second. So we know that 1 rotation per second times that by 2 pi. This is going to give us, why do I keep not using my finger? This is going to give us the radians per second. So, woo, didn't mean to blow up my camera there. There we go. I don't need to be that big. Okay, so basically this is just 2 pi, right? One rotation per second times 2 pi. It's just going to be 2 pi. So it's like 0.8. What's it again? Oh, 6.28. Yeah. Okay, so we're going to use 6.28 radians per second. Yeah, it's fine. Okay, so that was her initial, let me put that over 2. That was her initial angular velocity. Then over here, her mass does not change, but the radius did. Now her knee is only 0.35 squared over 2 times we're trying to find that final angular speed. So we just got to do a lot of multiplication here, do a bit of math. 4.5 times 0.8 squared divided by 2 times 6.28. So over here, we should get about 90 I'm going to go ahead and just write this all out. 432. Over here, got 45 times 0.35 squared divided by 2. And here we get 2 once again, I'll write this whole thing. I tend to, if it's only 5 or 6 or less decimals, I write the whole thing out for myself just because I don't want to round it off if it's only a couple decimals. So we'll go ahead and we will divide. So we should get a final angular speed, 90.432 divided by second answer, of 32.8 radians per second. 32.8 radians per second. We started at 6.28 radians per second. We ended up at 32.8 radians per second. Again, that angular speed increased because we decreased the R. We know this, again, we've seen it with the ice skater. As the arms come in, she really speeds up, and as the arms go out, she slows down. Again, we have this inverse relationship going on here. Now, we can actually talk about the angular momentum of an object in a linear path because angular momentum can be used to set an object into rotational motion. So that object, setting another object into rotation, does not have to be rotating actually to have angular momentum. What it does is it needs to be traveling perpendicular to the other object's axis. And again, we're going to talk about that, what that means in just a bit. But looking at this example, hopefully this will make sense. So we have a girl running towards a merry-go-round. Now, we wouldn't normally think of the girl having angular momentum because she's running in a straight line. We can talk about definitely her linear momentum at that point, but when she jumps on the merry-go-round, it is going to rotate. So her momentum transferred into the merry-go-round and caused it to rotate. So she actually does have angular momentum if she is causing angular rotation. But we look at the formula a little bit differently. So in this case, this is her angular momentum. Her angular momentum, yes. This is specifically the formula for when we are looking at an object traveling in a straight line. Her angular momentum is R times P, where we know what P is. P is the linear momentum. However, it has to be the momentum perpendicular to the axis. And again, we'll talk about that in just a bit. We already had to talk about that, so we just had to keep in mind, with rotating objects, we are talking about always looking at what is a force, or in this case, an object, perpendicular to the axis. You may have to do trig if it is not coming exactly perpendicular. And we know R being the distance from the axis. Now, I want to clarify this formula because I can't remember if I did this before. With talking about torque, We talked about how torque is RF, right? But the F specifically referred to a force perpendicular to the axis. The same thing has to happen here. So if you look in the textbook, I believe this picture actually in the situation was in the textbook. They give you a formula, you can see it right here, RP, which is what we just wrote down. Yeah. Times sine phi, that's what that is. It's actually not theta, that's phi. I'm not a huge fan of this equation because if you recall, sometimes the angle they give you is not the angle you need in order to use that formula. And so rather than being like, oh, well, I need to find the right angle, usually it's just a matter of subtracting by 90, but still, or subtracting from 90, I should say. If we can instead just remember that the P is in the direction perpendicular to the axis, then we can find that we may need sine, we may need cosine, rather than having to be like, oh, guaranteed it's sine, and then accidentally use the wrong angle. So I just wanted to clarify that again, you'll see that formula using sine phi. Just remember, the P is perpendicular to the axis. That's the one we're talking about. It may need cosine, you may need sine. So let's talk about the situation here, the merry-go-round situation. A girl has a mass of 30 kilograms. She runs towards the merry-go-round at 3 meters per second, then jumps on. So we have basically a collision, right? We've dealt with these before. The merry-go-round is initially at rest, has a mass of 100 kilograms and a radius of 2 meters, and can be treated as a solid disc. They are telling us what formulas to use for the rotational inertia for the girl and for the merry-go-round. So we want to find the speed of the merry-go-round after the girl jumps on. Camera around. So once again, we know this is conservation of momentum because we have a before speed and an after speed and basically a collision. So we're going to need to know a lot of information here. Let's start with our end goal. Again, we're trying to find the final speed of the merry-go-round. So rotation speed, so they mean angular speed. Angular speed of the merry-go-round, let's say. That's our end goal. Now, again, what we need, though, is that we're starting with the fact that the momentum initial, the total momentum initial, we should say, because they're separate momentums together, is going to equal their final momentums together. So let's kind of break some stuff down here. Initially, we have the angular momentum of the girl and the angular momentum of the merry-go-round, we'll say, initial. Then we have the, we're still going to put this, and there's a reason why we'll talk about here. We have the, actually we can put it this way, that's fine. The angular momentum of the girl plus the merry-go-round. We can put it that way, we're just gonna have to be careful a little bit later. Because again, they are one object at that point. They technically do have one angular momentum. It's just going to be a little bit different later. So let's start off by plugging in formulas. Now, this girl is traveling in a linear path. We are talking about her angular momentum, but she is traveling in a straight line. So look back to what we just copied. What would be the formula here since she is traveling in a straight line? Well, again, looking back to the slide we just did, since she was traveling in a straight line, we have R times P, and I'm going to go ahead and plug in the formula for P. So P is, again, her mass of the girl. Remembering, guys, that it's very important when we use these subscripts. The girl and the merry-go-round have different masses. Times the girl's initial speed. So that's our formula for the girl. Plus, the merry-go-round does not have any momentum. The merry-go-round, we are assuming, is at rest. I can't remember if it says. Yeah, it doesn't tell. Oh, there it is. Initially at rest. Yeah. Okay, so this is all the momentum we have before. That's going to equal our momentum afterwards. Now, let's kind of break this down here. they do have different rotational inertias. They are technically one object. So normally what we did, kind of thinking down here real quick actually, what we did when we had a sticking collision was we added their masses together, right? We had like the mass of the girl plus the mass of the merry-go-round times the speed. Well, in this case, again, it's not just masses, it's inertias. So when I go to plug this in now again, once they are rotating, now we are using the formula for angular momentum of a rotating object. So think for a second, look over your notes. What formula are we using now since they are rotating together? Well, let's all the way back again to what we said up here. That's their inertia times the angular speed. Now, again, their inertias are going to get added together. We have the inertia of the girl plus the merry-go-round times their final angular speeds. Excuse me. So when we do this, what's going to happen here, I'm going to rewrite this one more time. EGI equals, their inertias are going to get added together just like we would for the masses back when we were doing regular momentum. Now again, I'm going to go ahead and say finals here because those are going to change a little bit. Yes, technically we have initial rotational inertias and finals. So I'm going to go ahead and add a little F here. So we can do one more replacement with our formulas. And I want to see if you guys can go from here. Again, I'm just going to keep doing this. Don't need to be this big, computer. What are you doing? I want to see if you guys can kind of finish this up from here. So I'm going to scroll up. What we're going to do here is we're going to rewrite this one more time, replacing with the rotational inertia formulas. And then we're basically going to be able to plug everything in. So I'll scroll up here. Here's our rotational inertia formulas. Remember that the mass specifically refers to the mass of the girl is going to be over here. This is just the mass of the merry-go-round. Let's go ahead and give it a shot. See how far you go and then click continue when you're ready. Okay, so we have R, M, G. This is the initial angular momentum of the girl. Now over here again, we have the mass of the girl, radius squared. That was that formula. Plus for the merry-go-round, we have the mass of the merry-go-round, radius squared over 2. And we have W final, omega final, angular velocity final, whatever you want to say there. Okay, now this is what's kind of weird, but the R here is going to be the same because that doesn't change when she jumps from when she jumps on. Remember, this initial is literally referring to right before she jumps on. She's like midair. When she's midair jumping onto that merry-go-round, her radius, her distance from center, is the same as afterwards. Just for that split second, she is right there, just ready to jump on. We have the same radius. So we have a radius of 2 meters. So we got 2. We need the mass of the girl, because this is her momentum before, so 30. And her initial speed is 3. Then afterwards, we have the mass of the girl, which once again was 30, times the radius squared, plus mass of the merry-go-round is 100. Yes, 100 kilograms times radius squared over 2 times omega final. And then we just got to do a lot of reorganizing. Let's go ahead and kind of solve this through. I know this is 180 over here. What do we get on this side? We got 30 times 2 squared plus 100 times 4 divided by 2, basically. We should get 320 over here times their angular speed, divide 320 away. Okay, so 180 divided by 320, we should get 0.5. I'm going to just write this whole thing. 625. There we go. Radians per second. And there we go. So again, it's just a lot to keep straight. I would say definitely the hardest part about this is knowing when that you need to replace formulas. That's the big thing. I replaced a lot of formulas here, keeping them all straight. And again, understanding here that it's the inertias that are getting added together. It's not the masses. These objects, the girl has a concentrated mass and the merry-go-round is a disk. So they have different inertias, so we add those together rather than add the masses and use the same inertia formula. So be careful. If they happen to have the same inertia formula, you could add the masses together, but I'd recommend just keep them separate, add the inertias together separately, and then just be very careful as you follow down what you're plugging in where.